Well, good morning. It's a pleasure to introduce José Luis Cisneros Molina from the Institute of Cuernavaca, from Cuernavaca, the Institute of Mathematics of the University of Mexico. He's a very good researcher both in topology and singularities, and a very close collaborator of Pepe Seade. So he's going to continue the course that Pepe started on Monday.
Okay. First of all, thank you for the opportunity to continue Pepe's course. What I want to do is, well, go a bit more into detail of how the things Pepe said are proved. In particular, well, I'm going to do what my former supervisor, PhD supervisor, told me not to do some computations in public, but I will. So I'm going to go through Milnor's proof of his vibration theorem. I agree with David Massey that Milnor's books are fantastic. He writes very well. But with this book on singularities, I noticed that something happened. In fact, happened to me when I read his book. That is really well written. You follow everything. You understand what he's doing. At the end, you are convinced that you proved the vibration theorem. But somehow it feels that this was like magic. Like how he managed to do what he did. No? So what I'm trying to do today is more or less follow his proof and give a geometric interpretation of what he's doing. And in doing that, one will see that this concept of their regularity will appear there several times. So, and it was funny because when Pepe Yagüed and me work in this deregularity thing, so we found this condition in order to have equivalence with the vibration of the tube and the sphere. And afterwards I realized that it was all the time in Milnor's original proof. So the moral of this thing is that sometimes to do new mathematics, you have to look carefully into the old mathematics and just interpret it in a different way. Okay, so well, I remind Milnor's vibration theorem. So we have a holomorphic map. Okay, and we call B the preimage of 0. We will take a closed ball of a radius epsilon. Remember, small enough in order to have this conical structure. And, well, I'm going to denote by S epsilon just the boundary. And what else? Okay, so K will be the link. So is just the sphere minus B. Sorry, the B intersection with sphere. Okay, so Milnor's vibration is the following. So we have phi defined as F over the number F from the sphere minus the link to S1 is a locally trivial vibration. Okay. So to prove this theorem, as Pepe mentioned, basically we need to do two steps. The first one is prove that phi is a submersion, and the second is that phi is locally trivial. Okay, so we are going to do these 2 steps. So in order to do that, I need to recall some basic things. So let me talk about complex and real gradients. So basically, just this is notation. So Bn Wn, this is Cn. So I'm going to denote by this the Hermitian inner product in Cn. So all we know is okay, and also well, Cn can be seen as R2n, and we can see it as a Euclidean space, and the Euclidean inner product is just, so I'm going to note it by this, and it's just the real part of the Hermitian one. Okay. What else do I need? Okay, so now if we have a function, a holomorphic function, we define the gradient, the complex gradient. So is but we have to take here conjugates. Okay, and so this definition says the following: if we take a curve, so if we want to take the directional derivative of this function along the curve P, so in other words, we have df pt dt. So this will be dp dt grad f. Okay, so this formula is telling us that the directional derivative of f in the direction of the curve P is just the Hermitian inner product of the directional vector of the curve with the gradient. Okay, and well, and using this this definition, we can see that if we consider the gradient of the logarithm of f, okay, remember f is just locally defined as a single valued function, but if we use the definition, we will see that this is just grad f. Well, let me put f and set conjugate. And this is well defined everywhere. So the gradient is well defined everywhere. And we will be all the time working basically with this logarithm. Okay, so okay, so now again we consider our function, and well, as Pepe said, since it's holomorphic and 0 here is an isolated critical value, so we can find a neighborhood of 0 in Cn, such that when we restrict to that neighborhood, the only critical point is 0. So we are going to work in this neighborhood all the time. And so we write f just as the modulus in polar form. So this theta is just the argument. And well, from here we have two real analytic functions. So it's just the argument. This is just locally defined as a single valued function because, well, you can take several values the angle, and we take log of the modulus. Again, this is go to here. And of course, well, this goes because we have log f of z is just taking logarithm here. So in other words, this is just the imaginary part of the logarithm function, and this is the real part. Okay, so, well, of course, what we do now is, if we take directional derivatives, well, we get what we had before, the log f. So if we take, again, a curve, well, this will be the log f pg dt plus I d theta pt dt. Okay, so again, the directional derivative of this function along the curve P is just, well, its real part is just this directional derivative, and the imaginary part is this one. And, well, what we need to do is to see how these two things look like. So now, okay, so let's start with theta. So what's this? Well, okay, so this is a real analytic function. So we need to get the gradient, which will be the real gradient. So you need to use the real inner product. So, and also, I forgot to say something. Exactly, I forgot to say something. So I said this is the real and imaginary part. So, of course, this is the real part of this thing. But this is the imaginary part. So this is the imaginary part of log f set. But this is exactly, I can see it as the real part of I log z minus I log z, log f z. And that's what I'm going to use, okay? So, okay, so this then is the real part of this thing. So, of this thing. So d minus I log f z dt. But what is this? This is the real part of, well, so this is, well, here is pt dp dt, and here is graph minus I log f pt. Okay, but just using the definition of the gradient, is just very easy to see that this minus I goes into an I here. Okay, and well, so again, the real part of this Hermitian inner product is just the real, the Euclidean inner product. Okay, so this computation, what it's saying is that the gradient of this real function is this vector here. Okay, so I'm going to write it like this. grad R of theta is just I grad log f. Okay? So now if I do the same for the other function, we get something similar. So is v log fp t dt. This is the real part of the log d log f dt, well, fpt. And just this is and that's it. This is again and so the gradient, the real gradient of log of the modulus of f is just okay. So notice that this vector, as real vectors, this vector is orthogonal to this one, no? Because here we are multiplying by I. So they are always orthogonal. And well, and what is the point of all this? Well, we have the real gradients, and what is the main property of the gradient vector field? It is orthogonal to the level hypersurfaces. Okay? That will be the main point. So what we are going to do now is see which are the level hypersurfaces of these two maps. Okay, so with the first one, so we take just theta not real, and I'm going to denote by L theta not plus. Just is, well, instead of writing it's just better, is the real ray, so this is the complex numbers, this is the real ray with angle theta naught with respect to the positive real axis. Okay, so what we do is we take this, but what is this? Well, this sets in u minus b, such that set is theta naught. Okay, so this is exactly the sets. Sorry? Sorry? Theta value of f? No. This is set because the map goes from Cn. Yeah. Okay. You're. You're right. Yeah. Well. Is in the way I define it. So like this, of course, is set is f of set, but I'm denoting theta of set, the argument of the image. So this is just okay. So are okay these points such that exactly f of set lies in this line. Okay. because in this line, all the points in this line have this argument, well, in this ray. So this is basically the inverse image of the ray, okay? And well, so I'm going to denote like this thing. Well, this thing is just notation, okay? Again, since outside V, F is a submersion, this will be a codimension, real codimension 1 submanifold in CN, or in our boundary neighborhood U. And the same thing we do for, well, let me draw a picture. So we have B here, we have complex numbers here, we have our ray like this. And so what I'm taking is the pre-image. Of course, look at that in the closure of this ray here is the zero. So we have something like this. So is what it projects to this ray. Okay. Now here we take the disk of radius delta in C. And so what we're going to do is take log and I'm going to take log of delta. So it's this point here, of course, that log f of z is log of delta. So this is, so it's delta, and of course this is just of the boundary of delta. So this is what Pepe called the tube. Yes, that's what I said. I choose. So F is holomorphic. F. And it has 0 as a isolated critical value, so I'm removing B. Outside B is always a submersion because the critical points are in V. Yes, so this is a isolated critical value because it's holomorphic, and I'm taking just restricting my function to a neighborhood such that this is the only critical value, so all the critical points are in B. So outside B is always a submersion. And again, well, because it's a submersion outside B, it will be also a codimension 1 real submanifold. So what we have here is now this is the circle of radius delta, and what we get is our tube. Okay, so this is delta. Okay, so now what we want to do is, okay, so basically, well, let me just draw them. So that means that if I take a point here in E theta naught, well, this is like the level hypersurface of theta, so that means its gradient is I grad log f, okay? Because it's the normal to this thing. And if I take a point in the tube, then the normal is grad log f. Or in other words, if I take a point in both of them, so here is I grad log f of z, and here will be grad log f of z, and remember these two are orthogonal. Okay, so now we want to prove that the map f over the modulo of f restricted to the sphere minus the link is a submersion. Okay, so how do we do that? Well, first I'm consider big phi from u minus b to S1. Okay, so, well, just given, again, f modulo of f, okay? So, and, well, the first proposition, which is o lemma, is the following. This phi is a submersion. Okay, which is, well, obvious because this is, phi is just apply f and then apply pi, with pi is okay, it's just the projection of the complex numbers minus 0 to the circle, and outside B, both are submersions, so the composition is a submersion, okay? So if we consider this map we are interested in, but in the whole neighborhood U minus B is a submersion, okay? So what we want to do is to see when, so remember, we are interested in the small phi, which goes from here to S1, okay? So in other words, this phi is, small phi is the restriction of this big phi to this sphere, okay? So, okay, so what we need to do is, what are the fibers of this big phi? Well, so we can see in this drawing. So this is, remember, big phi is f. So if we have some point set, it goes to some point f of z, which is not 0 because we are outside B. And then we project, well, let me put it here. And then we project to the circle, okay? So the fibers is, if I take a theta in the circle, or e I theta 0, so the inverse image under pi is just the ray, and the inverse image over f is e theta 0. So in other words, what I'm saying is capital phi of some point in the circle is precisely e theta 0, okay? So this means that if I take in some point set in u minus b, and I take the differential of capital phi, the kernel of this differential is precisely well, let me put it like this. Okay? So, because since this is the fiber of phi, when you take the differential, the kernel will be the tangent to this submanifold, okay? So in order to see that this, what are the critical points of this restriction, so you see this, the sphere is codimension 1, real codimension 1, and also E theta is real codimension 1. Okay? So what is a critical point of here? Of course, when the differential of this map is not a submersion. So since the dimension 1 is when it's 0. Okay, so that means that the tangent space to a point here, so let's take here, so Z is a critical point of small phi when the tangent space to the sphere, well, in general is contained in this kernel, but since both are codimension 1, coincides with the tangent space of this thing, okay? But what is this telling us? Well, this is telling us that, well, if these two tangent spaces coincide, that means that the normal vectors, so if you know a normal vector in each of them, they are, one is a real multiple of the other. So that means that the normal to this one is a real multiple of this. So in other words, remember, what is the normal vector to this? Well, the gradient of theta, which was I grad log epsilon. And that means that there exists some real or the normal vector to the sphere is Z. We can take Z itself. And this is precisely the first lemma in Milnor's book. So I'm going to write it down. So, okay, well, so let me just write it. Lemma. So, well, lemma goes here. Okay, Z is a critical point of phi if this happens. Okay? Okay, so okay, so what we need to prove in order to see that phi is a submersion, we need to prove that there is some, sorry, this is here, some radius small enough such that this doesn't happen, okay? This is what we need to do. But before, let me, so in order to reinterpret these things towards seeing how appears the irregularity, let me just add some notation. So remember, we have here C, and we took the ray L theta plus. So let me call L theta the whole line, okay? So in other words, L theta, of course, is the same as L theta plus pi, because I can take the angle all the way around here. And let me call x theta, as Pepe did, just the preimage of this line. So what we have is x theta can be seen as the union of three things: E theta, V, and E theta plus pi, okay? So this is the preimage of this ray, this is the preimage of 0, and this is the preimage of the other ray, okay? And then, as Pepe mentioned, these are real analytic hypersurfaces, because, well, of course, this can be defined, just apply F and then project in the orthogonal plane to the line, or well, in this case, it's the orthogonal line, and this is the preimage of 0, and this collection is what he called the canonical pencil Okay. Canonical pencil. Okay, so what is saying this formula here? Well, it's saying that the critical points of phi are the points where the canonical pencil and the spheres are not transverse. Okay, so we can say this in other way. Z is a critical point if exactly x theta is not transverse to at that point. No? Okay, and well, and you can see now immediately what I was saying, because this is the first part where Milnor is telling us, consider d-regularity, because remember, d-regularity was the following. You have the canonical pencil, and the function is d-regular if there exists a small enough radius such that all the spheres center of the origin contained in this sphere are always transverse to the all elements of the pencil. Okay, so, and if that happens, that means that there are no critical points of phi, which is what Milnor proved, and I will try to do right now. Okay, so, okay. Okay, so what we need to prove is the following. There exists epsilon 0 such that for every set in U minus B with normal set less than epsilon 0, the vectors, well, set and I graph log f set are linearly independent over R. Okay? This is what we need to prove in order to have that this, not only that this phi is a submersion, that so all these phi's with epsilon less than epsilon naught are submersions. No? Okay. So, and as I said, this lemma is equivalent to say that there exists epsilon naught such that for all the spheres smaller than, with radius smaller than epsilon naught, the canonical pencil is always transverse to all the spheres. And so to prove this lemma, what Milnor did is prove a slightly stronger lemma, which is the following, which is the key to basically all this fibrillation theorem. So that for all set in U minus B with zero, the two vectors again set and I graph log f of set are either linearly independent over C in this, and or else we have grad log f of z equal lambda of z, where lambda is a complex number such that the argument of lambda is less than pi over 4. Okay? So it's easy to see that this lemma, let me call it key lemma, that the key lemma implies this thing. Why? Because if they are linearly independent over C, of course, they are linearly independent over R. Okay? And if this happens, so the only way that I grad log of f of z is a real multiple of z is that this lambda is a pure imaginary complex number. But what we have is, by this condition of the argument, that means that this lambda lives here, inside this open region, so it cannot be pure imaginary. Okay? Okay, so, well, to prove this, the proof of this is just a very nice application of the curve selection lemma. And I'm not going to go into detail of this because basically, well, it's not related with this geometrical interpretation I want to do. So if you want to see curve selection lemma, well, it's in the appendix of David Massey's lecture notes. Of course, it's in Milner's book. But so just believe me that this happened. No? Okay. But this is really the key lemma because this lemma allows to do 3 things. Well, the first one is, well, if we assume that we have it, this implies this, so we have phi is a submersion. Okay, so the corollary is that phi is a submersion for every epsilon less than epsilon 0. Okay? Also, this same key lemma will be the thing that will allow us to prove the second part of the theorem, which is local triviality. And also, the same lemma will allow us to prove that the vibration in the sphere and the tube are equivalent. So this is really the main point. Okay, so what else? Okay, so let me just say another thing, another remark. So remember that this small phi was the restriction of capital phi to, so this is the restriction to this. Okay, this is phi. And remember that what the fibers of capital phi are the E theta. Okay? So what are the fibers of this? So let me take here a point in the circle. The fiber, which is, I'm going to denote it just like this. Well, it's precisely this intersection, no? Because this is the restriction to this, so this, the fiber of this is the fiber of this restricted to this thing. And since it's a submersion, and I said that a submersion means that these two things, so the canonical pencil and the spheres are transverse, so this is a transverse intersection, and the transverse intersection of two manifolds is a manifold. Also, of course, this is a manifold. But also, we already knew, because since it's a submersion, we know that all the points here are regular values, so the inverse image are submanifolds as well. So, but this is the relation between the two. So the Milnor fiber, so this is the Milnor fibration. The Milnor fiber is just the intersection of this, well, one of part of the canonical pencil with the sphere. Sorry?
Or not?
No.
Okay, just the opposite.
Yes, it's the inverse image of the ray without the origin. Okay, so now, what we want to do? Well, we want to prove local triviality. Okay. So the fibers are something like this. So this is the link, and the fibers go something like this. Okay, so you can see this as you have the canonical pencil, so remember, so here is like 1 E theta, and the intersection with the sphere gives the fiber of phi, small phi. So we have this canonical pencil like this, you get all the fibers. And so then the idea now to prove local triviality, well, is to construct a vector field here in the sphere, which projects to the unit vector field in the circle. Okay? So in that way, it will be this vector field transverse to all the fibers, and the idea is to take the flow in order to move one fiber to the neighboring fibers. Okay? So we need to, how did I call it? Well, so suppose you have, suppose we have a vector field. Let me say one word, complete. Vector field. W here. So, okay, which projects onto the vector field U on S1 given by, of course, U of EI theta is I EI theta. Okay. So basically, okay, so if we have this, take again now an integral curve of this vector field. Of course, these curves depend not only on t but also in the initial point. Okay, so Milnor denotes it by P of t, the note is like ht opposite 0. So ht is just a diffeomorphism from S to itself. So So with this, well, we have the local triviality is very easy because then we take in the circle and we take W small neighborhood of this point in the circle. So that means I'm taking here this, and I'm taking just small neighborhood. So local triviality is just given by this. We take the fiber over this point, and we want this, and well, this is EI theta plus T, comma Z. Well, of course, it will go to H T of Z, and this will give, and this will be a diffeomorphism, and we will have local triviality. Okay. So I wrote here suppose. So we don't have already the vector field. So how do we construct such a vector field? Well, in principle, it's easy because since we proved that this map phi is a submersion, well, take this vector field and take a lifting of this vector field. You can lift it, okay? But there is some slight problem, which is this thing. Because since the sphere minus the link is not compact, we need to ensure that when you take a integral curve of the vector field, it does not go into K in a finite time. Okay? So for any finite time, it will remain inside. So that's the delicate point we need to address, and we will. Okay, so okay, so what I say is we need to ensure that P of T cannot tend to K as T tends to T naught, a finite value of T. But this is the same thing as asking that we need to ensure that f of P of T cannot tend to 0 as T tends to T naught. But it's the same as saying that we need to ensure that log f P of T does not tend to minus infinity when T tends to T naught. Okay? So we are going to do this. And how to do this? Well, so basically we need to control so we want this to grow or decrease slowly. So basically we need to control the derivative. Okay? So suppose we ask this d log f pt dt is less than 1. Okay? So we are asking that the absolute value of the derivative of this thing is less than 1. So what we get is this thing, log f p t naught minus log f p t 0, sorry. This is what? Well, this is, of course, Okay, and this is okay, but this is less than because we ask this. Okay, so this means, of course, that this logarithm cannot go to minus infinity in a finite limit time because is less. The difference will be always less than this finite number. Okay, so we ask this. We are done. We ensure that the integral curves cannot go into K. Okay, so this is one thing we need to ask. Of course, we need to ask this, that it projects into this vector field U. Okay, so that means that if I take the integral curve, well, so when we compose it with phi, we'll get these loops here with constant velocity 1. Okay, so that means that theta of P of t will be t plus some constant. Okay, so, and this is equivalent, well, so take the derivative. So, okay, the constant 0, this is 1, so that this derivative is 1, okay? But remember that this, what is this? Well, this is the real part of dp dt of I graph log f of z, okay? So we are asking that this, the real part of this inner product is 1, okay? And also, I'm going to write like this. What this means, well, remember, this is real part dp dt graph log f of z. Okay, so we are asking these two conditions. Okay, so let me write it down carefully. So in other words, we need, so in summary, we need W such that, so we need a vector field W in the sphere, or well, in fact, okay, so I'm going to say like, we need a vector field W on, let me construct it in the whole neighborhood minus B. Yes. Yeah.
In your right side, is equal 1?
Here?
Yeah.
Yeah.
But it seems something is not.
Why?
The result father was saying that it's less than 1.
Yeah.
And now you are saying that this is equal 1.
Yeah, but the point is here is with an I.
In the is
Without.
Oh, without. Okay.
So it is exactly what I'm going to write here. So we need three properties. So first we need the real part of W with Z is 0. Okay? This means what? Well, this means that it's tangent to the sphere. Okay? Okay, because this is remember the real part is the Euclidean inner product, so that means it's real orthogonal with Z, so that means it's tangent to the sphere. The second is what I wrote there, graph log fz less than 1, and this is complete. So it does not go into k in a finite time. And 3, I need now with I equal 1. Okay, and this is projects onto U, then U is this vector field here. So, okay, so we need a vector field with all these 3 properties. And so let me give you the idea on how to get this, the geometrical idea to how to get this vector field, and then I will tell you how Milnor found the explicit vector field which does this. So I think I need this drawing. So I need my tube. Okay. Okay, so now okay, so I need a vector field on the sphere. Okay, so let me take a point here, set, and then let me take the sphere of radius. So let me take the sphere of radius norm of set. Okay, so this point is contained. Okay, so the normal vector to the sphere is set itself, and we have the normal vector to the tube is the real gradient, which is grad log f of z. Okay? We know that these 2 vectors cannot be linearly dependent over the reals, because that would mean that this point set is a critical point, and we prove that inside these small balls we don't have critical points. Okay, so they cannot be collinear real collinear. Okay, and so what does this mean? Well, yeah. Uh-huh. For what?
In front of the gradient of log z.
Uh-huh.
Over there in your picture.
Uh-huh. No. I'm
I grad log fc is real, linear independent over c. Right?
No. Well, you're right. You're right. You are right. Yes, you're right. The linear, yes. The critical points is when they are real collinear with I. So you are right. So sorry. So let me see why this cannot happen. Okay. So let me say it like this. You're right. So okay. So well, the normal to the sphere is set. The normal to the tube is here without the I. Okay. And okay. So the key lemma of Milnor says that we have 2 possibilities. Either, yes, these are linearly independent over C, which implies the so I grad log, and yes, so case 1. So is set and I grad log linearly independent over C. Okay? But of course, grad log is in the complex line of I grad log. So this cannot be in this complex plane. So in this case, yes, this cannot be real linearly independent with this, dependent with this. Okay? And in that case, okay. So the normal to this vector is the tangent space of the sphere, and the normal to this is the tangent space to the tube. And both have dimension 1. And these are not real collinear, so that means that both of them generate the whole ambient space. So that means that at that point, the tube and the sphere are transverse. Okay? So that means that if you take the intersection, it will be some submanifold of the sphere, and it's a submanifold as well of the tube at the same time. Okay? And let me see. Okay, so what I said here is that Z does not lie on the complex generated by this grad log. And also, okay, so they are collinear, they are transverse. Okay, so of course the vector field, so you have this transverse intersection, and you get a submanifold, the intersection, and the tangent space to this small submanifold. What it is? Well, is the orthogonal plane to the real two plane generated by these two vectors. Okay. So what you do? Well, the idea is, well, so I need to see just one more thing, because this submanifold, it can happen two things. Okay. Let me. The drawing is very small, so let me amplify it. So we have the tube, well, we have the tube, we have the sphere, which is very ugly sphere, and also we have here E theta of Z, okay? So, okay, see, this will be like, and we have also our big sphere. So the point is that exactly. So the tube and the sphere are transverse. So you have a small submanifold. So of course this submanifold is in the sphere, and can happen two things. That we have the bad luck that this submanifold, or the tangent space of this submanifold, let me call it, well, the tangent space is just T intersection with T Z, the tube F of Z, okay? That the tangent space to that submanifold, which is the intersection of these two, coincides with the tangent space to the fiber on the sphere. That's one possibility, and the other is that it does not. Okay? I need to tell you why in this case we cannot have this. Let me see why. Okay. Let me see. So, okay, let me see exactly. So suppose this happened, okay? That this, so if you take a vector in this intersection, also lies here. But remember, this, the tangent, so this is, so the fiber of this is just E theta intersection the sphere, okay? So of course, so this is a vector in the intersection of the tangent space of the sphere and the tangent space of E theta. This already knew because we have here, but if it is also tangent to E theta, that means that this vector is orthogonal to the gradient of E theta. So this is orthogonal to E grad log f of z. And yes, this is, so if we have E grad log here, it will be orthogonal, and that okay, so it's also so it will be orthogonal to Z, orthogonal to the tube, and orthogonal to the exactly. So it's orthogonal to three things: the sphere, the tube, and E theta. Okay, but well, this is and this well, so this is a transverse intersection. We have a very nice manifold here, and it has codimension too. Okay, so that means that this tangent space is of dimension 2. So it's a plane. So it can. So what I mean is, since it has to be a fortiori dimension 2, that means that it cannot happen the three things at the same time. Without being two of these linearly dependent. So that will imply that this set will be in the plane, complex plane generated by these two, which is not the case in the case we took. Okay, so then the idea is to take our vector field W of Z in this small submanifold. Okay, so this will imply what? Imply condition 1, because it's tangent to the sphere, will imply condition 2. Why? Because since it's on the tube, and the tube is the gradient, the tube is the level hypersurface of this, of the map log modulo of f. So that means this inner product, if you are in the tube, this inner product is 0. So of course 0 is less than 1. So if we choose the vector in this submanifold, it satisfies these two properties, and we just need to ask the vector, well, so we need to choose inside this small submanifold a vector which satisfies the third property, no? And this is what Milnor did. So, and, okay, so I think, well, tomorrow we'll give Milnor's proposition, but that's the idea. Now, in the other case, so they have the other case that grad log f of z is lambda of z with argument of lambda less than pi over 4. In this case, what will happen is that this intersection coincides with the tangent space to the fiber. So we cannot take a vector there, because we want the vector field be transverse to the fibers in order to prove local triviality. So what Milnor does is he chooses a very appropriate vector field that, well, I will tell you tomorrow. And as you see, so these geometrical properties, everything boils down to have conditions in the inner products. So when you read Milnor's book, everything is about inner products with I grad log f of z or grad log f of z. And if you don't interpret what is going on, you can do all the computations, but you don't see what is behind. No? Okay, so is what we. So let me just to see what we are going to do tomorrow. Write what we are going to prove tomorrow. Okay. Okay, so it's lemma. If epsilon is less than epsilon naught, then there exists a smooth vector field Vz on u minus v. Well, actually is here, such that Vz is tangent to this, and for each set here we have this. Is non-zero, and the absolute value, its argument is less than pi over 4. Okay? Okay. And well, so if you read this, of course, it's not immediate that it satisfies these three things. But we will see that the way that Milner constructs this with these properties, it will have those properties there. So, okay, so, let me see if I have 15 minutes, so maybe I can say something about that. Well, we need to go to the proof because, look, there is something I did. Here I wrote V, and here I'm calling it W, okay? So the vector field that this lemma gives us is not precisely the one we need. We will get some vector field. Of course, we are going to construct it again in the two cases, when these vectors are linearly independent over the complex line, or when there is this linear dependency. So we have two cases. In one of the cases, it will satisfy the three properties. In the other one, it will satisfy just one, but then we need to normalize it. And once we normalize it, then we get the whole thing. So that's why we cannot see directly that this vector field given by the lemma satisfies these things. Okay. So tomorrow I will prove this. And then what we need to do is, well, because someone told me that the members of the audience asked that I explain what is the Tom AF condition, because it has been mentioned many times and no one said what it is. So I will say what is the Tom AF condition and how to use it to prove the vibration on the tube. And then again, using this key lemma by Milner, we're going to construct this vector field which inflates the tube to the sphere. And again, when we see this vector field, again, this will tell us, consider transversality of the canonical pencil to the spheres. So again, the irregularity appears there. Okay, so thank you very much. We have some questions?
Well, the way that Milner proved the existence of vector field satisfying those three conditions is just considering the projection of the I grad log Fz in the tangent space of the sphere, the tangent plane of the sphere. I think that's enough.
The projection of which one?
I grad log FZ
Uh-huh.
in the tangent plane of the sphere, in each point. I think this is enough. And normalize, of course. You should normalize it. Just consider the projection, normalize it. I think so. But I have to, of course, you have to take care of the things.
Yeah, okay, I think about it tomorrow.
Sure.
If it's done that easily, and it's easier. Yes.